Welcome everyone to today's One World IAMP Mathematical Physics Seminar. This is a regular event hosted by IAMP, the International Association of Mathematical Physics. We are always looking for new members and also new members for this mailing list. Okay, today we are very happy to have Sven Bachmann, and he's going to tell us about tensor categories and quantization for the quantum Hall effect. Sven, the floor is yours.
Thank you very much, Hal. Thanks for the introduction and thanks for the invitation to speak. I spoke in this very seminar, I think 5 years ago. It was at the very beginning of the pandemic. And it's strange to find myself again speaking here. And paradoxically, so Hal asked me to speak specifically about this topic, which is a direct continuation of what I was talking about 5 years ago. So I'm very happy to be here. I'm going to talk about joint work with Matthew Corbelli and Martin Fraas, who are at UC Davis, and Yoshiko Ogata in Kyoto. So let's get started. So really, this talk is going to be in a general setting of two-dimensional quantum lattice systems, either quantum spin systems or lattice fermions. And I will spend quite a bit of time at the beginning introducing basic things, such as what it means in this setting to insert a magnetic flux, what we mean by charge transport, because at the end of the day, I want to talk about the quantum Hall effect, which is, it's about transport of electrons and electrical currents. So I'll spend a little bit of time on that. And then I'll move on to something a little bit more abstract, namely how to talk about these systems in infinite volume and what it means to have superselection sectors. And once I have this, I will discuss what it means to braid quasi-particles, move them around each other. And as a consequence, I will finally talk about what is in the title, namely the quantization of the quantum Hall conductance. Now, since it will take me quite a bit of time to introduce basic objects and so on, and the actual results will come at the very end, I decided to give a summary at the very beginning. So if people want to just listen to the summary and leave, that's fine. Really, what I want to talk about is the quantum Hall effect, and there's sort of three results that I would like to discuss. The first one is, how do you construct quasi-particle excitations that happen to be abelian anyons? So we'll have a ground state. Everything is at zero temperature here. So we'll have a ground state, and you'll have excitations which are localized. That's what I call quasi-particle excitations above the ground state. I'll explain how to do that in the context of the quantum Hall effect. Then, if you have quasi-particle excitations, you can move them around each other. And upon doing that, if you have bosons, nothing happens. If you have fermions, you pick up a minus sign. And if you have anyons, you may pick up other phases than just pi. And we'll be able to compute this and actually relate that quantity, so the phase you pick up when you move one particle around the other, to a very physical quantity, which is the quantum Hall conductance, which I will denote kappa through this little relation here. So that's the first result. Braiding phase is related to the conductance of charge. And the last thing, which is a well-known fact, experimental fact, that the Hall conductance is quantized. Low magnetic fields is quantized in integers. At high magnetic fields with interactions between the particles, it's quantized in a fractional way. And one question is always to explain not only why it's quantized, but what are the possible values of the Hall conductance. And we're going to get an answer here, which is the following thing. And I'll have to explain a little bit these words, but a sort of vague way to say this is that if I have P prime types, fundamental types of quasi-particle excitations, then in fact, the Hall conductance will be of the form, it is a rational number, which is of the form Q over P, where P is at most P prime, namely at most the number of quasi-particle excitations. Okay, so this is one way to explain the quantization of the quantum Hall conductance. Okay, so these are the three results that I would like to present, and I'll have to go a little bit more into details to explain all the symbols and the meanings of what happens on this slide. So, overall, what I'm always going to have in mind is the following setting. So I'm in 2 dimensions. I have a lattice. So, at the end of the day, everything's going to be in infinite volume. But for this first slide, because I want everything to be, defined in the simplest possible way, I take a finite subset of my lattice Z2, and I have a Hamiltonian. Let's think of fermions. It's easier to picture, I think. So you just have a finite range Hamiltonian. When I write this, I mean, look, this is just a sum of terms that might be hopping terms or interaction terms, these 5x. 5x is just the hopping or the interactions between fermions on the sides of little x. X is a subset, right? All the interactions are self-adjoint elements. And for simplicity, it's not necessary, but for simplicity here, we can think that this is just, finite range. And the important assumption, I want to talk about charge transport. Talking about charge transport, if you have, for this to really make sense, you have to have charge conservation. Otherwise, charge can be created and annihilated, and I don't want that to happen. So always, all my Hamiltonians here are going to be charge conserving. By this, I mean, you see there's a charge operator, which is the sum of the number of operators at each side of the lattice, and the interaction terms commute with the charge. Okay, so all my Hamiltonians are going to be charge conserving in the following way. If you want a very concrete example, it is here at the very bottom. You see you have some nearest neighbor hopping. You have some interaction here, that's the density sort of interaction. Again, it's written in a nearest neighbor fashion. It could be longer range. That doesn't matter, but just for to have something concrete in mind. And there might be an external potential of this form. Okay, so you will see what I will do here. It will not depend on an explicit Hamiltonian. It's so there's going to be rather assumptions, conditions on the Hamiltonian without having something explicit in mind. But this one here is just a concrete example. All right. So now, one thing we want to do is to talk about magnetic fluxes, and so in particular, I will need magnetic vector potentials. So let me try to explain how to, it's very basic physics, but sometimes it's, we kind of forget how to do this. So what is a vector potential in this lattice setting? It's a function on the edges of my lattice. So you see, I will make drawings like this one here. The drawing looks like it's in the continuum, but of course you always have to imagine that all of these are, there's a lattice posed on these surfaces. So a vector potential is just a function on the edges of a lattice, and what will be important for us is the flux across a loop. So the flux, the magnetic flux across a loop is just so you have like this one here. A lattice is put on a torus, so here on the plane, which will be more akin to what I'm going to do later. You can imagine here a loop on your lattice, and the flux across this loop. Well, you just sum. You go along that loop, and you just sum the vector potential along these along all the edges of that loop. In the continuum, it would just be a line integral along that loop, and that would determine the flux through the surface that is supported by that loop. Okay, so you see, if I was on a torus, I could thread a magnetic flux inside the torus. What I will do more today is pierce, like here, so pierce the 2D plane by a flux, which is localized at one point. So that's what it means to have a magnetic flux. What it means at the level of the Hamiltonian, right? I had here a concrete Hamiltonian. At the level of the Hamiltonian, one way to think about it is just you sort of twist the hopping terms by this. So the hopping terms, I wrote them with xy are 2 points, but if they're nearest neighbor, this is also an edge, right? So I also write a of xy for that. And you just twist the hopping term by the magnetic potential like this. And this is what it means at the level of Hamiltonian to to add a magnetic field or magnetic vector potential to the Hamiltonian. Okay, good. Now, as we probably all remember from basics physics, how do you get a flux? Well, one way to get a function on edges of the lattice is by picking a function on the lattice sides and then defining a function on the edges, which is just a difference, sort of a derivative. Okay, so that if I have a function theta that defined on my lattice, d theta is certainly a function on the edges defined like this, right? Now, of course, if I have this, the function is a well-defined function on the lattice sides. I sum the contribution along any curve, just because it's a function, it's telescopic, and the sum of a closed curve is always 0. So there's no flux. So if I have a function like this, which I could call an exact, the magnetic flux is always 0. Nonetheless, they will be useful. That's why I want to talk about that, right? So that's a simple thing. How do I get the magnetic flux? Well, it cannot be written as the sort of derivative of a function on the plane, but here's one which I will use very much. In fact, I mean the notation. Of course, it looks very complicated, but it's just a function which is 0 everywhere on all edges of the lattice except along the negative half axis, the real half axis, if you want. So it's just a function which is 1 across all, I would have a line here is, let's say, the origin here, okay, and A is just 1, across all the edges that would be here along. Okay, that's this notation. Okay, and it's 0 everywhere. So in particular, if you have this and you make a little loop around here, it's 0 everywhere except when you cross that line where you pick a +1. And so the flux associated to that half-line gauge potential would be exactly 1. Okay, and of course that A, I cannot write it as a derivative of anything. Okay, so that's the sort of flux that I imagine. This is exactly on the plane of flux that pierces the plane, right? Exactly at the origin. Right. Now, what does that exactly mean in terms of a second quantized Hamiltonian? As I wrote before, with A and A stars. Well, I mentioned, this is about twisting the hopping term. An easy way to think about it, which is slightly different, is by looking at the following equalities. So if you have an annihilation operator and creation annihilation operator up there, you can check, by just taking the derivative with respect to phi here, that you have that sort of quantity. It's a little calculation. So if you take an A and you conjugate with the number operator, you just pick up a phase. Okay. Now that means that if I take my Hamiltonian as above, right, which had some terms A star A, and you conjugate by that sort of unitary e to the I phi, and here I wrote, this theta q is just, I have this function theta that I introduced before, and at each site, this makes sense, right? The number operator at that site multiplied by the value of the function theta. If you do this, well, you see, for example, let me just go back to the original, the Hamiltonian, just to have something in mind. You see, if I do this on that sort of term, right, the A y will pick a phase theta of y, the A star x will pick a phase minus theta of x. And so this term here, I will add a phase, which is the difference of theta of x and y, which is exactly changing the value of the hopping term, right? And so, at the level of a Hamiltonian, if I have that sort of gauge potential A, which is given by a d theta, it's just, it's just obtained by a unitary transformation. It's a trivial transformation of the Hamiltonian, which I can obtain like this. Okay, and if you so really I hope I managed to somewhat convince you that if I take a Hamiltonian of the type I gave you before and I twist it by these operators, the only terms in the Hamiltonian that are going to be changed are those that are along the support of d theta, so the change of theta. Okay, and so I'm going to do that a lot, and the one that I would always consider is the following function. you see it's just an indicator function of the upper half plane on the lattice, okay? And so really this corresponds to having a change d theta only along the horizontal line. And it corresponds to, if you want, so this allows me to introduce this notation here, Q up. This is the charge in the upper half plane, okay? So if I conjugate my Hamiltonian by this unitary here, this would just twist all the terms of my Hamiltonian that are hopping across the horizontal line, right? Now, of course, maybe some of you are already thinking, well, is this operator well defined? Well, in fact, not quite, right? Because the sum of all charges in the upper half plane, this is an infinite sum, which is certainly not convergent. So this is a bit, that is a little bit of a formal thing at this point, right? I will take care of that in a second. Okay, just to insist again, if I do that sort of thing, right, with that particular potential here, then there's no flux, right? In order to have a flux, I would need to do the same thing only on the half line, not on the full line, and we'll learn how to do this. Good. So since I'm talking about the Hall effect, I have one slide about the Hall effect at the very basic level. So you see here, I draw the plane, the 2D plane as this disk, but you can imagine that to be infinitely extended, right? And I said, well, all I've done so far is try to say, okay, I know how to introduce a magnetic flux, okay? Of course, I can make that in a time-dependent fashion, right? I can make my potential time-dependent, and so I can make a time-dependent vector potential, therefore a time-dependent flux. Now, Maxwell's equation, in fact, the particular one, which is Faraday's law, tells you the following, that if you have a time-dependent flux here, that will create an electromotive force that goes around the flux, okay? So that's Faraday's law. Time-dependent flux yields an electromotive force. So the electrons that are moving in my plane, would like to move like this in circles around the flux. Now, if on top of the original flux, I have a perpendicular magnetic field that is, now it's just constant field everywhere on my plane, that's this B, then because of the Lorentz force, you have, the movement of the particle, the velocity will actually go, in the perpendicular direction. So instead of going around the flux, there's going to be a current that goes, from the origin out to infinity or the other way around, okay? And that is the Hall current in this setting. So the Hall current is a current that goes from the origin away out to infinity, okay? That's just the combination of Faraday's law and the Lorentz force. Again, there's different settings for the quantum Hall effect. This is somewhat of a, there's two main settings really. One where you try to drive a current by a changing magnetic flux. This is the one I'm using here. There's another setting which is trying to drive a current by just an electric field. The whole thing looks a little bit different, but whenever these things can be compared, of course they give the same results. Okay, but for today's talk, I'm always going to use the setting that I sketch here at the physical level. Okay. All right. So that's the Hall effect. So that's kind of a physical little break. Let's make a mathematical break. Precisely, I want to have all of this sort of well defined. So what is the setting, the concrete mathematical setting I have in mind? What I have in mind is, okay, it's the algebraic approach to quantum mechanics, where I start with an algebra of observables, which is the algebra of canonical anti-commutation relations. These are fermions, okay? So these are these objects A of F, where F is a one-particle Hilbert space. Here, the typical Hilbert space would be little L2 on Z2. Maybe there's some internal degrees of freedom, Cn. And these A's anti-commute like this, right? The anti-commutator of AF with A star G is just the inner product of F and G, where F and G are one particle wave functions. Okay, that defines my algebra. This together with the fact that all A's commute with each other, all A stars commute with each other, anti-commute with each other, and there's an identity. Okay, that gives me an algebra of observables. Now, so far I talked about the Hamiltonian. I gave an explicit Hamiltonian, which was expressed in terms of creation and annihilation operators, exactly that sort of guys. So if I want to go to the infinite volume limit, again, this sort of sum over nearest neighbors, they're certainly not convergent as elements in the algebra, right? Because they live everywhere along the plane. So as an operator, that doesn't exist. But as a dynamics, there's a well-defined dynamics in the infinite volume. I will not go into the details, but really, this is one way to think about this. So to construct it, you take any observable A. Now you take a Hamiltonian in a finite volume, a strictly finite volume. These sums are finite, so everything is perfectly well defined. You look at the Heisenberg dynamics of that observable, right? So that's perfectly fine. And then you ask the question: can I now take the limit, the infinite volume limit? Okay. And the answer is yes. The standard way to do this is to use the Lie-Robinson bounds. I'm sure there were already many talks in this seminar about it, so I will not go into details, but this limit exists provided that the Hamiltonian is sufficiently local. And then that defines the dynamics on the whole algebra. So it's the dynamics in the infinite volume limit. So we have the observables, we have a dynamics. And what are states in this business? Well, states are expectation values. So positive normalized linear functionals over the algebra. So they're in the dual of the algebra, if you want. I will denote them by omega. So again, they are expectation values. Right? They're not vectors in a Hilbert space. They're just expectation values of observables. Now, one way, absolutely classical, to in a sense come back to Hilbert space setting is to use the GNS representation, which I will do once in a while in this talk. So you can always, construct a representation pi. As if you're given a state, you can construct a representation pi, which takes abstract elements of the algebra and make it and represents them as bounded operators on a given Hilbert space, such that the expectation value of A is given like this. So there's a particular vector in that Hilbert space, capital omega, which does the job. Okay, that's called the GNS representation. It's an old but very useful result. Right. So the last two things, again, this will play only a sort of minor role, but I just want to briefly say this. Of course, I don't have vectors in my my states are elements of the dual of the algebra. And so what is a ground state? Well, you still have a dynamics. You can make sense of a ground state of a given dynamics. And there's an expression for it. Here it is, right? So if I have a tau which is generated by a Hamiltonian, then in fact, and I'll come back to that a bit later, the commutator of the Hamiltonian with a local observable makes sense. And then you can ask for those for the state that satisfy this inequality, and that is an equality that defines a ground state. If you've never seen this, it looks a little bit strange. If you've seen that, well, you know it. So maybe I won't insist. And but for example, in the GNS representation, this would really mean that there's a Hamiltonian that is bounded below, and the GNS vector is the ground state vector of that Hamiltonian. But otherwise, really, the only thing that matters here is that you remember that there's a notion of a ground state in this algebraic setting. And in fact, there's even a notion of having a ground state that is spectrally isolated from the rest of the spectrum. So there's a spectral gap of above the ground state energy. Again, it has a formula which is like this. It's all really variational characterizations of ground states and excited states, but expressed in the algebraic setting. So there's also a notion of having a ground state above which there's a spectral gap. A ground state energy, above which there's a spectral gap.
Sven,
okay.
Are you here assuming that the ground state is unique also?
Yes, absolutely.
Okay, yeah.
Yes. Mm-hmm. Good. So, okay. So having all of this in hand now, from now to at the end of the talk, I'm going to consider a state and a dynamics, and the state is a gap ground state of a charge conserving Hamiltonian. Okay, that's the general setting that I have. And let's think, now let's pick a subset Z. I think of charge Q associated to that subset. It's just the sum of the charges that are cited within that subset. Now you see, if Z is not the whole lattice, even though the Hamiltonian is invariant under the charge, the state itself will not be, because there's going to be, you know, if you take only a subset, there's going to be charge fluctuations around the boundary of that set. So, you know, here's my finite set. The charge in the ground state is not, you know, the ground state is not an eigenstate for the charge in that finite set, but there's something which you can fairly easily prove, which we did back in the days, and really it comes from a work of Hastings originally, that, you know, if you have the charge in the set Z, you can construct an operator K, and that will play an important role, K, which is supported only on the boundary of that set, right? Which makes it such that Q minus K now has the ground state as its eigenstate, if you want. So the state, you know, again, this is just the algebraic way to write this. The state here, omega, is invariant under the action of taking the commutator with Q minus K. If I was to write this in the GNS representation, so in the Hilbert space setting, that would just mean that Q minus K applied to the vector state omega would be 0, or at least an eigenstate. Okay. So that means, although omega is not invariant under Q, omega will be invariant under this operator Q minus K, which I will call Q bar. And it's important that K is supported only on the boundary. So really, this is an expression of the fact that, sure, the charge is not conserved on the ground state, but the charge fluctuations are just local. They're just somehow localized around the boundary of my set. Okay. In fact, more can be said about this K. Again, it's an explicit construction. K, again, looks like some sort of Hamiltonian, if you want. It's a sum of local terms. And they're such that, you know, the interactions here are non-zero, provided, you know, they contain both terms in, you know, they touch, you know, they cross the boundary here. So I don't have any interaction terms between electrons far out here or far out in here. And these Ks, again, these interaction terms, they're very local. They're not strictly finite range, but you see that their strength, the norm of K of X, decays faster than any polynomial. This is the meaning of this expression in the size, in the diameter of the set X. Okay, so really K dz is a sum of terms that are, we have to think about it, that are essentially localized along the boundary of the set. Okay, that's a little construction. In fact, this is a bit more general. You know, I talked so far about Hamiltonians, and to have something concrete in mind, that they were finite range. In fact, we always allow for something a bit more general, which have that sort of the same sort of structure. So you have an interaction, which is a map from finite subsets to elements of the algebra, where the norm of these elements of the algebra becomes small when the sets becomes large, right? So this is interactions that become weak at large distances. And once you have this, you can always generate a family, a dynamics, if you want, which solve the standard Heisenberg equation. I write it in this fashion because these G's here may, in principle, even depend on time. That would still be fine, right? And just a quick comment, precisely this commutator of G and A, again, G is a sum of terms, so G itself does not really make sense, but that makes sense, you see, because if A is a local observable, because this decays fast, you only see those terms here that are not too far from the support of A. And so you show that that the expression here on the right is well defined for any local observable. All right, and you know, as I had here, you know, this KZ, again, these terms have to touch here the boundary. I would say that this is anchored on the boundary. Any interaction may be anchored on a particular set, and that's what it means, right? If the interaction terms are 0, if they don't touch the given set. Right, good. So let's come back to flux insertion. You know, so if I had in particular finite set, just to make this calculation here correct, you know, I can make a little transformation, little gauge transformation, e to the I phi qz on the vector. Okay. Now you see I've introduced these operators q minus k, which leave the state invariant. Okay. So I can insert that for free here, right? And if I insert that for free, I give a name to that whole operator here. I'll call it f. Right, so f has on the ground state has the same action as just a gauge transformation. But let's look at f. You see, it has an explicit expression here, and you see that q comes here with a positive sign and here with a negative sign. So if you look at how it's generated, you take the derivative with respect to phi of this thing, you see that. I mean, this is just a sort of interaction picture, if you want. The f of phi has a generator, and it's generated by this k of phi, which is the k before, which is supported on the boundary of the set z, which is just conjugated by e to the I phi q. Okay, but again, you know, this operator here, so k dz, will be localized along the boundary. And this is really important, right? If I make a gauge transformation like this, you know, qz lives on the whole bulk of the set z. But its action on the ground state can be represented by this operator f, which itself is just an operator which lives on the boundary on the set, sort of a string operator that lives on the boundary of the set z. Okay? So I can implement a gauge transformation on a set with a bulk by only acting on the boundary. This, of course, as long as I live as this acts on the ground state space. And in fact, if you look, there's even something even easier. At phi equals 2 pi, you see q, you remember q is made up of charge operators. This is an operator which has integer spectrum. So at 2 pi, phi is 2 pi, this little bit here is just the identity. Actually, at 2 pi, right? This just disappears. And so f at 2 pi is just given by e to the minus 2 pi I q bar. This q bar being q minus n. Okay. So this q bar, now, you know, why do I write all of this? It's some just silly calculations. Well, it shows the following, that this operator q bar here, so q minus k, I introduced it, but just to explain that, you know, fluctuations of charge on the ground state are local, but in fact, you know, it's exponential. In particular, 2 pi just gives me, you know, what it means to do a gauge transformation on the ground state space. And this finally allows me to say how to actually how I will actually introduce flux. So what I'm going to do is, you know, I again have this picture of a disk for the whole plane. So I can look at the charge in a half space. Okay, that's q up. Associated to that, I can construct the corresponding k. This one will live on the boundary of that half space, which is just a line. Okay, this thing is a sum of terms, the little q, which are anchored along that line. And I can of course construct the q bar, which is q minus k. Okay. And now, so, and you know, I insisted that, you know, maybe 15 minutes ago, that this does not insert any flux. So in order to insert flux, I need to have just a half line thing, which I can do. I just, you know, this is a sum of terms, so I only keep the terms that are on the half line. Okay, that's this expression here. And that is a good interaction if you want. I can look at the corresponding automorphism, and that gives me the state with a unit flux inserted at the origin. And this state differs from the original state. Again, I act on it only along that line. So it differs from the original ground state only along that line. I will actually think about it that it really, there's a little cone. I hide this line inside a cone. And that's these two states are essentially equal to each other outside the cone, and they differ inside the cone. Now, here's something, maybe this is a little bit too computational. I'm running a little bit behind on time, so I'll not say this, explain this too much, but, you know, this is always like this, you know, the line, if you want, it's like a branch cut in complex analysis. The line, I can put it anywhere. It doesn't matter. What matters, the only physical thing, is the flux at the end of the line. And indeed, if the flux is inserted along line L1 or along line L2, well, in fact, there's always a unitary that moves the line from one to the other. This is an explicit construction, which maybe I won't explain, but you can move. So this is the important thing, is this line can be moved. If I, let's say, fix the origin, I can move the line, and I can also move the origin a little bit. That's just an explicit calculation, again, that you can make here. So these lines are transportable, I will say. Okay. Now, very briefly, you see this Q bar, I insisted, is the generator of flux insertion. Okay, now because it's only along this half line. Now, how do I compute charge transport? Well, I need to look at the change of charge inside, let's say a half space, and I want to look at how much charge flows across this boundary. The way to do this is just to look at the commutator of Q bar, which is the generator of charge of flux insertion, and in fact Q, but it's easy to convince yourself that because it's within this commutator, I can just as well put Q bar. So this is the infinitesimal change of charge due to flux insertion. And what is that? Well, that's exactly what Hall conductance is. Okay, so I have an expression for the Hall conductance in terms of these Q bars. And this is something which is, in fact, related to my talk 5 years ago. You can show, and this is not completely trivial, that this is equal to the commutator, the expectation value of the commutator of the Ks, which then is associated to adiabatic curvature, which, if you're in the quantum Hall business, is also the Hall conductance. Now, I'm just going to warn everyone here who's trying to follow this. All of this, you have to be very careful, because these terms, this is Q bar is a sum it's an infinite sum. So these commutators are in principle very tricky. They do not, these sums don't converge in any good way. They certainly, it's only because you are within a commutator and the commutator within a state that all of this makes sense. And so you have to be very careful. And for example, one thing you could say is you could say, hey, Sven, you told us, 5 minutes ago, that a commutator of Q bar in a state omega is always 0. You see, it's still, where is it? It's a few slides ago. More than 5 minutes ago. What is happening? Sorry, I cannot move my, where was this? Here it is, right? Omega of Q bar of anything is 0. Sure, but that's only when this acts on an, here it's not Q bar on an observable. It's a commutator of 2 Q bars. So it's typical of these expressions that are formally 0, but in practice they're not, and in fact they will happen to be quantized. You see, it's the same as in an index of a pair of projections, if you know that. It formally looks like trace of U star PU minus P, which is formally 0, but that's only if everything was trace class. It's the same sort of expression here, that you have to be very careful when you play with these expectation values of commutators of these sort of interaction terms. Good. So now I have this state with the flux inserted, and I can think of the corresponding GNS representation, which is obtained from the original ground state representation, upon which I act with the flux insertion automorphism. Now, as I said before, the state, and therefore also the representations, they differ from each other only inside the cone. Okay, and in fact, I can put that cone anywhere. So this is the meaning of this expression. If I take the ground state representation and I look outside any cone, it's actually going to be unitarily equivalent. There's a unitary that to the state, and therefore the representation corresponding with the state having a flux inserted. Okay, that's just a fact that you can observe by this from this construction. Okay, so if you I can pick a cone, hide the string inside the cone, and outside of the cone, the state looks exactly as the ground state. Now, this is something which again comes from the construction, but is actually very well known. This was introduced by Doplicher, Hagen, Roberts in a series of papers in the early 70s, when they were trying to understand or have a sort of a general definition of what it means to be a quasi-particle state. And this was, you know, specifically for this sort of picture with where you have cones and strings that extend from a point to up to infinity. This was really developed a little bit later, and this is what I want to talk about now. So now somehow I've just talked about inserting flux, but now more generally, I could ask the question: okay, can I try to classify all of these states or all of these representations that satisfy that criterion? So they look away from a cone, they look like the ground state. And these are the ones I would like to call quasi-particle states, right? So this is the task that you can try to do in mathematics. Can I classify all of these representations that satisfy this DHR criterion? In fact, we'll give a name to the equivalence classes of such representations. They're called superselection sectors. Okay, so when I say superselection sectors, you can think of these are the elementary quasi-particle excitations above the given ground state. And it turns out in 2D, you can do this in a completely abstract setting. You can show that naturally in 2D they may be anyons, so particles that when I braid them around each other, I pick up, let's say, a phase, so a billion anyons. And this program was really, you know, worked out in details in the 80s, originally by Buchholz and Fredenhagen, 82, and then in even more detail, Fredenhagen, Rehren, and Schröer in 89. So where they really, you know, they really answer this question. Let's look at all representations that satisfy this criterion with these strings. What can we say about it? Can we classify them? Do we see anyons? And this is all completely answered in these papers that are written in the framework of relativistic quantum field theory. Now, here I'm in quantum lattice systems. In quantum lattice systems, there's a kind of a fundamental difference that the locality is not the same, right? So there's no a priori relativistic locality. So these, you know, the causality that is given in relativistic quantum field theory is not there. But of course, there's something which looks a little bit the same, which is the Lieb-Robinson bound. You know, what does it tell you? It tells you that if I start with an observable which is localized in a let's say at a point, then the dynamics associated to that, when it corresponds to some sort of local Hamiltonian, the dynamics will increase, you know, the support of that observable, but really essentially only inside a sort of light cone or sound cone, as people say, right, up to tails. So there's always these tails. It's not strictly localized in cones, in space-time cones, but always up to tails. And this is technically a problem. But you can still say, well, with this, can I use this instead of the strict locality of quantum field theory and construct, you know, in a sense, redo this work here in this setting that applies to condensed matter systems? And the answer is yes. And this is this theorem of Ogata, 2022, where you know, what does this say? It say, well, if you start with a gapped ground state, there's an extra condition which I will not talk about, the Hague duality here. But if you do that, then indeed you can classify all of these representations that satisfy the DHR criterion, namely they look like the ground state away from cones, and they have a nice structure, the structure of a braided C-star tensor category. This is work. By the way, in concrete models, this can be done with kind of by hand, and there's a very recent work here for a class of models called the Kitaev's quantum double models. Good. So maybe I spend a little bit too much time. So let's see. So let me just explain a little bit what is this category. So this category, it has, you know, it has objects like the elements of a set, and these are these representations satisfying the criterion. Okay, these are the elements, if you want, of my category. Now, in a category, there's also morphism, so maps between these objects. Here, these maps are intertwiners of representations. So things that do that, right? T here take the representation pi1 and maps it into the representation pi2. So these are the basic objects of the basic elements of this category, the representations and their intertwines. Now, it's important. It will be important for us that we can introduce a product of objects. You see, I can create a particle and a second particle. Okay, that's a product, so to say. In general, it's a bit of a mess, but if your representation, like they do in our example, in the quantum Hall flux inserted problem, if they come from, you start from the original representation and you act on it with an automorphism that I call rho here. Then there's a sort of natural product. Is how do you you just compose the automorphisms, okay? And I will denote that the product representation with just this tensor net, okay? It's just rho tensor sigma. So you know how to make a product of objects, namely the product of representations, which now I've defined as the product of the corresponding automorphism that generate them. What is the product of the intertwiners between them? Well, that's just a little exercise. And you see that the product of, if you have an intertwiner representations sigma prime given by S between rho and rho prime given by R, then the product of the intertwiners, that's just a calculation using this. It has an expression. I just want to write this to show that it's not just simply SR. The R is inside the S. That's why there's an extra sigma that shows up here. Okay, but there's a good way to determine here a product of representation, a product of intertwines. Now, I insist that this is just a caricature because otherwise this would be all simple and easy. It doesn't quite work like this because not all representations are of this form. And if they're not, then things get a little bit complicated. And because just a lack of time, I will maybe skip this, but there's some much more complicated constructions that need to be done in the general setting. The only thing that I would like to say that, one of the results of the construction is that you can construct any such representation can be obtained, it's the other way around by first applying the ground state representation and then applying an automorphism afterwards, which is the other way around than before. And all of this really is not on the same algebra as a bigger algebra, but I will just skip that, okay? There's a lot more work to construct this category, and this is the work that was done in the context of quantum lattice system by Yoshiko Ogata. And we have, as I said, right, we have, this criterion. What does it tell you? It tells us that these strings can be moved from one place to another in a unitary fashion. Namely, it means that if you look outside of any cone, you can always, or rather the best way to think about it is, I can always move a string inside a cone. If I pick a cone, I can move the string inside the cone. So you see, that gives me a way to talk about moving strings around. Okay, these unitary intertwiners that really show up from these from the DHR criterion. I mean, they're not intertwiners, but they map pi to sigma and sigma to pi outside of a cone. So I can put these strings in any cone. They allow me to move these strings, and this is really the important thing here. Having this, now I know how to move the strings. Okay, and again, there's quite a bit of work to actually do all of this really properly. But having this, you can start asking the following question. Let me create a state or representation that has two particles, let's say a rho and a sigma, right? Two of these strings. And now I can start moving them around. And again, this is not us, right? This was introduced certainly in the Buchholz-Friedenhagen paper back in the days. You can construct a braiding, which really means I take two particles and I exchange them, right? The formula is not particularly important, but really there's an expression, and you can check that it intertwines between two representations, rho tensor sigma and sigma tensor rho. So this, there you see that it really corresponds to exchanging two particles. I just, in the original papers, there's no limit. Here, I really need to take this particle here and send it out to infinity. That's again because of this not exact locality of the setting in condensed matter as opposed to relativistic field theory. And the one which will, it's a slight expansion on this. It's a full braiding, if you want. the formula is a bit the same, but one of them, before you start braiding, you move it to a cone, move that cone out to infinity, and then braid the whole thing. That's an expression, but that defines what we call the statistical phase. Okay. So that's in that abstract setting, I can talk about braiding particles around each other. And it's then here's a little proposition. This phase is really, well, maybe the first point is not so important. The second point is the important one. I call it a phase because it is a phase. In principle, it's an intertwiner, so it's a unitary operator. No, here it's just a phase. So that's why it makes sense to call it a statistical phase. That's for those representations that come as they do here with the flux inserted operators as actual automorphism of my algebra. Now these things are invariant. I can change the particle locally, so act on it with a unitary. If I don't move them around, it doesn't change the phase. And the important thing for us is the additivity, which is down there. So if I braid a particle sigma around rho 1 and rho 2, the phase that I pick up is the product of the phases. I mean, the product of the sum of the phases, if I think of the phase, or if I think of the complex number, is just a product. So all of this, again, there's an assumption here which applies for the representations that I obtain from this flux insertion procedure. And I can finally, state the theorems. Let me just remind you. So I have these flux insertion operators alpha that come from Q bar. They generate, these are the flux insertion automorphism. The representations I'm talking about are, you take the ground state representation, you act upon it with that. And the result is that this braiding, which I just obtained, this is just, I know is a phase, and it actually is given by an exponential of the Hall conductance. Okay. Again, is it so strange? Well, maybe not, right? Because think of the following thing, pi L, I can think of this as having, I have two particles, one with the flux, let's say here, the other one, the flux line there, right? And what do? I take this one and I just move it around the other, right? And if I do this, these operators are only localized along the edges. So really, this is the only thing that happens is here close to that intersection point. And there, what do I see? Well, just the commutator of the generators, which is a commutator of Q bars. But a commutator of Q bar, as I said before, it actually gives you the Hall conductance. So this little picture is a little bit of a sketch of why you can prove this. I mean, the proof is a little bit messy, but this is the fundamental reason. Okay, so braiding is related to Hall conductance, and the second thing is quantization of the Hall conductance. So now we know. So these superselection sectors, these are these representations that correspond, that satisfy the DHR criterion. In fact, I consider only those that are irreducible, fundamental ones. Okay, and so if there are only a finite number of such irreducible superselection sectors, so really strictly speaking, these are equivalence class of irreducible representations, then the Hall conductance is quantized in this unit. So it's a rational number and quantized like this. The proof of that is simple enough that it's a line, right? You see, if you have one of those representations with a flux inserted, I can take n of them. It's still an irreducible representation. And so, but there's a finite number of them in total. So eventually I will have to come back to myself. So eventually there's a P for which I have to come back to it has to be the ground state representation again, or unitarily equivalent to the ground state representation, right? For, at most after P prime, there's not more irreducible representation. So I have to come back to myself. But then you see the braiding using pi 0 has no particles. So there's no braiding. So that phase is 1. But pi 0, well, it's unitarily equivalent to pi to the tensor p. And I said that this sort of unitary equivalence does not change the phase. Now I have this additivity property that the phases add up. So this phase is just p times the original phase, pi. This one is e to the 2 pi I, the whole conductance. So here is e to the pi square I, the whole conductance. So I get this extra factor p here. And now you see that one is e to the 2 pi p times 2 pi kappa, which means that 2 pi kappa has to be a rational number, or p times 2 pi kappa has to be an integer. Okay, so that's how you get quantization from this finiteness of the number of superselection sectors assumption. Now, so far I haven't given you references, but I think it's time to actually do it. So first of all, there's a good old references of the physics literature. You know, the first, this really comes from Laughlin, who realized that fractional quantum Hall effect had, fractionally charged particles. This is in his original paper of '83. And just after that, Halperin and Aravas, Schrieffer, and Wilczek observed that these Laughlin states were anyons, had fractional statistics. So this is, this was solved in a sense, finished in the early '80s in the physics literature. In more of our sort of approach and a bit slightly more mathematical nature. So I already talked about these papers here. They don't have specifically to do with the Hall effect. They're more general. The goal is to construct and classify these representations that satisfy the DHR criterion and observe that they satisfy Braiding group statistics. Now, if you look at specifically what happens for the quantum Hall effect, there was a lot of push in the 90s, in particular around Fröhlich, to take quantum field theory approach and similarly understand all possible quantum Hall conductance, all possible fractions using topological quantum field theory. So you see, this is a long effort, which is very parallel to ours, but different in the sense that it doesn't start from microscopic models, but the approach is quantum field theoretic in nature. What is closer to what we did here, starting from microscopic systems, really started with Hastings and Michalakis. This was the integer quantum Hall effect, although they have a paragraph saying, oh, this all works for fractional as well. We had a similar work in 2020, which again, I refer to my previous talk. I mentioned this in my previous talk at the IAMP seminar. So both works here these are large but finite volumes. So we really work on finite tori and take the limit L to infinity. Okay. There's just after our work and using ours, there's the paper of Kapustin and Sopenko. They work in infinite volume in the full plane. And to prove quantization, they also prove quantization, but not using finiteness of superselection sectors, because this language was not even there at the time. But they have another assumption which goes by the name of invertibility. I'll not go into that here. So since time is short, let me conclude here. So I presented a theory of some fractional quantum Hall states, not all of them. In fact, these were only abelian anyons. There's more out there, but this was just about that. Starting from microscopic models in the infinite volume limit. And I would like to point out that I made assumptions that typically I have a ground state which has a spectral gap. These assumptions are very difficult to verify. So these are conditional statements, and the assumptions would be very difficult to. If you give me a Hamiltonian in infinite volume in 2D, it's very hard to check that it has a spectral gap. But under these assumptions, we know how to construct quasi-particle states that corresponds to inserting a flux. So it's in a sense that inserting the flux binds a state, okay, or moves the state from infinity there. With that, using the language of this category theoretic approach and algebraic approach to quantum field theory, we could relate the braiding to the Hall conductance. So the phase I acquire while moving these particles around each other is proportional to the Hall conductance. And with that, we could obtain a criterion to explain quantization of the Hall conductance, just due to the fact that there's a finite number of superselection sectors, namely a finite number of fundamental elementary particles above the ground state space. And I think I'll stop here. Thank you for your attention.
Thank you very much, Sven, for the wonderful talk after 5 years. Okay, so now let's have questions and comments? Anybody, please? You can just unmute yourself and ask questions. Okay, so probably let me ask some questions. So on this slide you said that to verify the assumptions can be very hard.
Yes.
And you only mentioned the spectral gap. I can imagine how hard it is, but is this the most difficult assumption to verify? You also have to verify assumption about the existence of superselection sectors and
right. So indeed. So there's really two things. So the gap assumption is very hard, and as far as I know, except for non-interacting systems in 2D, there's only one example where you can prove the gap. It's the works of Young, Nachtigall, and Sims and Warzel. No, not Sims, Warzel on the long cylinders, right? Where they can prove the existence of a gap. Otherwise, it's all conjectural for realistic models of quantum Hall effects. Okay, so I think it's still fair to say that this is a difficult problem.
Yes.
The other thing that you need is what I call the approximate Hague duality. And that's it's the same thing. This also plagues, in a certain sense, the algebraic approach. In quantum field theory, it's very hard to if you give me a model to prove that it satisfies this condition, which I never wrote right in the talk. But it's an algebraic condition on commutants and double commutants, and this is very difficult to prove. In fact, I mentioned here. You see, there's the work of Ogata here assumes this Hague duality. And this work here does not assume it, because in some examples you can actually do things by hand, right? And construct all of these superselection sectors kind of by hand, because everything is very explicit, and obtain the same sort of structure without having to use this approximate Hague duality. So this is, in fact, these quantum double models. These are the only case that I know of where all assumptions can be checked to, and this braided category can be constructed explicitly. Unfortunately, that doesn't really apply. Doesn't apply at all, in fact, to quantum Hall effect. The Hall conductance for these models is 0.
Okay. Any other questions, comments, please?
I may have a question.
Sure, Gil.
Yes.
Are there quasi-particles with only abelian or also with non-abelian braid statistics?
So in this, we've made some assumptions, right? So the answer is only abelian here. This is only abelian, right? I know, and this is why in my conclusion I also said that this is not general. It's only for some, in a sense, the easiest of the whole systems where there's the anyons are abelian. It comes really through this assumption here. Algebraically, this is the assumption that implies that the phase here is just a number indeed, and we don't really know how to deal with non-abelian anyons at this point.
And then for the abelian case, what's the progress relative to older investigations?
Well, again, I mean, I think,
so I'm sorry, I'm asking
no,
questions.
I mean, I think it's the progress is that the starting. I mean, I don't know if you want to call that progress, but it's the starting point is somewhat different, right? Here, the starting point is you start with a lattice, with a microscopic lattice system, and
but the physics is not on a lattice. I mean, it's just not on a lattice. You see that
right. Well, then I have to say that then that means that there's not progress, but walking backwards maybe. But to me, there's also this construction of these states with these string operators that construct explicitly representations that satisfy this property, that are relevant for quantum Hall. This is a slightly different starting point and construction. And that's where the news is, in a certain sense. That's all. I mean, as I said, I in fact mentioned your papers, Jörg, where these are much more general, right? But the starting point is slightly different.
Okay. Any other questions, comments?
Yeah, I have one.
Oh, yes.
Yeah.
Oh. Hi, Sven. Thanks for the nice.
Yeah.
So do you get some constraints about the possible values of the fractions you can observe, or you get all the fractions?
No. So again, this is also completely from this point of view here an open problem. Again, the older investigations answered some of them, but here for us the only constraint we get is the one which is displayed here, right? Which is if you assume that you have a finite number of superselection sectors, then you know that the fraction here, the denominator, is at most that number of superselection sector. In fact, you would expect that it's equal to it. If you were in finite volume, this was a little bit the reason why we started thinking about this. In finite volume, that P corresponds, put your system on a finite torus, then you have in general a ground state degeneracy, and then the P down here would be the number of ground states on the torus. And precisely, it was a little bit our question, if that's nice, but it's a very much finite volume sort of thing. What replaces this in infinite volume? And in infinite volume, it's this finite number of superselection sectors. Now, again, how do you prove that a given model has a finite number of superselection sectors? It's a difficult question.
Okay, but you get all possible Qs in your.
Yeah, that also. I mean, we don't get any constraint on the possible Qs. It would be great to say more, but in this approach, we cannot.
Okay, but do you think there is something missing So what in the sense, why don't you get constraints on Q? Is there some missing assumption or missing ingredient?
No, but I mean, as you can see, somehow the proof is very soft, right? It's I mean, we don't. Sure, there would be missing assumptions probably if you wanted to say more. I mean, this is extremely general or vague depending on your preference. So yeah, we just don't have tools to say more and to say anything about the possible values of the Q, of the integer, the numerator. Yeah, this is completely missing in this approach. Again, other approaches have more to say about this.
Okay, thanks.
Yeah, actually, I also wanted to ask the relation between P prime and P. So this intuition sort of suggests that P should be equal to P prime, or
yes, that's right. And I do not know. Again, that this is an artifact of the proof, which is very simple. It's just
So
P prime is just say there's a finite number of them. That's all. That's all. Okay, and maybe here more could be said, but we didn't quite get there.
Okay, so it could be that P equal P prime, and you're still missing something.
Sure, absolutely. In fact, I think I would expect that P equals P prime. Yes.
Okay.
Yeah.
Right. Any other questions or comments? If not, okay, let's thank Sven for the wonderful talk again. Thank you very much.
Well, thanks for your attention.